Okay, I think we can go ahead and start the class. I received a couple of emails about the attendance and homework submission. There are some people who have tested positive for COVID, which happens a lot actually in all of the classes. And if you end up testing positive, or for whatever reason, if you couldn't come to class, just send me an email with your submission before, with your homework submission before the class. And if for whatever reason you couldn't submit your homework in time, again, send me an email and get an extension. And otherwise, bring your homework to the class and just give me a hard copy. If you are going to submit your homework through email, make sure, make sure to create a PDF file. Don't send me a bunch of pictures. Like, put all of them in a beautiful PDF file, and it should be fine. So I think the last thing we talked about was the equation, the hydrostatic equation, as a function of temperature, right? So this is the last equation we dealt with, the integral of dp over p negative g over r dz over t. So this is something that this was essentially the hydrostatic equation for a compressible fluid flow. This is better. So the idea was, if you are dealing with a gas, you can actually rewrite the equation to get to this. The left-hand side, you can take the integral. This will become natural log of P2 over P1. 1 and 2 are just different 2 different points inside your gas. And then we came up with 2 different conditions for temperature. One where temperature is not a function of altitude, so it is constant, or isothermal condition. So when you increase the altitude, your temperature is not going to change. And the thing that we are going to see today is where there is a linear relationship between temperature and the altitude or the height. Right? Since we are mostly dealing with gases, we are going to mostly deal with the altitude instead of height, right? In compressible fluid flow. But for the isothermal condition, we ended up getting this equation. Pressure at point 2 is going to be equal to pressure at point 1 exponential of negative g over r T naught or T0, which is your constant temperature. This doesn't change with altitude, and Z2 minus Z1. Okay, this was the case for the isothermal condition. But for the linear relationship, we first have to find the relationship. We first have to get an idea on how the relationship would look like. Essentially, in general, let's say we are talking about a linear relationship. So it will be in this type of form. T and at temperature changing with altitude, it actually Can be in this type as well. But the point is the relationship has to be linear. We need to have a baseline. Let's say it doesn't pass through 0. All right, a baseline. What is your temperature at Z equals to 0? Okay, and then we need to have the slope of this line. So two things: temperature at altitude 0 at the surface of the Earth, and then the baseline from your mathematics. We are gonna call that baseline temperature T of A. We're gonna call your slope of this line beta. Okay, and then multiply by Z, which is a simple mathematical relationship, a linear relationship between temperature and Z. And it can be actually plus beta Z, but the convention is always to get this negative. We're going to talk about the standards here as well a little bit. And if you're dealing with the surface of the Earth up until some altitude, which is actually up until altitude of 11 kilometers, this beta in SI is going to be 0.00065. There are two zeros. Always get this right. And the dimensions for this is kelvins per meters. So this beta is essentially the slope of our line, or the rate of change of temperature with altitude. Yeah. In the British system, it is 0.0037 degrees Rankine per feet. So in order to find a solution to this integral, we had to find a relationship between temperature and Z. It can be isothermal, or it can be a linear relationship, or it can be a more complex relationship. We don't really care about the more complex relationships at this point, and there's a good reason for it. The reason behind it is what we call the standard atmosphere. Okay, it's what we call a standard atmosphere. What is a standard atmosphere? A standard atmosphere is essentially a normalization of the values you're going to get at different altitudes for temperature and other properties throughout the Earth, that as a function of altitude. So this standard atmosphere is going to give you the value of pressure at 20 kilometers above the surface of the Earth, right? And that is supposed to be the same value throughout the Earth. It doesn't matter if you're in China or in the United States, right? You should get the same value when you are 20 kilometers above the surface of the Earth. This is not a true assumption. The idea is we have standardized the whole thing. The whole idea is to come up with a standard value. So we are essentially measuring an average value for that pressure or temperature at that specific height. Okay. So this gives us the ability to find a general function that relates temperature to the height. And you can see we can have different layers that represent different layers of atmosphere. Up until some point, we are going to see a linear temperature change. As I said, it is up until 11 kilometers altitude. Then we are going to get to an isothermal layer. So after some point, the temperature won't change with altitude. Then there will be another layer in which you will see a linear change, a linear increase, and so on and so forth. Right? So this trend will continue. The point is, using this standard atmosphere standardization method, we are essentially finding the relationship between temperature and Z, and we see it is constructed of different relationships, but all of them are isothermal or a linear relationship. So these two solutions work for us. We don't need to make things more complicated, right? We don't need to find complex, like polynomial relationships between temperature and the altitude. Does this make sense? Okay. So we already have the solution for isothermal, the constant temperature with altitude. We need to plug this in and take the integral. Let's plug it into the main equation we have. We are going to get a natural log of P2 over P1 equals to G over R integral of dz over Ta minus Bz, beta z. So if you take the integral, eventually you're going to come up with this relationship. And let's say, since we are dealing with the surface of the Earth, let's A to 1, let's do 1 and A here. So your P at point 1 is going to be equal to, if you take this integral, this is what you're going to get. PA multiplied by 1 minus beta Z over Ta to the power G over R beta. So as long as you have the temperature at the surface of the Earth, you have the pressure at the surface of the Earth, you should be able to calculate pressure at an altitude. Well, what should you do? Let's say you're dealing with a problem. You want to solve a problem that is in the third layer of the atmosphere. How should we approach this type of problems? Hopefully, we'll solve an example of this. But I just want to mention a methodology, the general method you want to use. So let's say temperature Z. And we want to find the value of pressure at this point. We only have the values here, right? PA and TA. And we have the betas, the slope of these lines. This one doesn't change, so we don't need to have the slope of the line. What you need to do is to start from here, find the pressure at this point using the value of temperature that is given to you on this plot. Then find the pressure at this point and use this point as your baseline for that equation to find the pressure at this point. Does this make sense? So essentially, you have to have 3 steps. You cannot just plug in the values in that equation and using PA, these values to get the pressure and temperature or whatever you're looking for here. Does this make sense? Okay, so let's move on to the next topic, which is the pressure measurement methods. Most of this chapter, we are going to focus on how to measure pressure at different situations for different conditions. Okay. One of the more famous pressure measurement devices is called the manometer. The manometer measures the pressure essentially using the same concept, right? The pressure is a function of height of a liquid or a fluid or gas in general, right? And we talked about the millimeters of mercury or water. This is what a regular, very simple manometer would look like. In your case, the idea is pressure at the surface, and we have talked about this before, pressure at this surface and this surface are the same. So let's say that there is this point inside, point 1, and the surface outside is called surface 2. The idea is pressure at point 2 is equals to pressure at point 1, right? So using this, we should be able to find the atmospheric pressure. I'm going to call it PA, right? How should we do that? If you recall from chapter 1, we had this concept vapor pressure, right? Which was essentially the equivalent to saturation pressure. And what it told us was that if you have this type of setup, you're going to get a vacuum type thing here, very close to vacuum. And the pressure you're going to feel here is called the vapor pressure. But since it's close to vacuum compared to the atmospheric pressure, we're just going to neglect it. The only thing we're going to get from here is the height. The idea, so based on this, the general formulation is going to be the atmospheric pressure is going to be your gamma multiplied by this height plus the vapor pressure. The pressure at point 2 and point 1 are equal. So PA plus P2 has to be equal to P1 plus gamma H plus P vapor. P1 and P2 will cancel out because they are the same. And this vapor pressure is usually very small. So we're going to assume it's 0. So this manometer is going to help us measure the atmospheric pressure using the height of this column of mercury. Any questions so far? Let me ask you one question. Why do we use mercury? Why don't we use water? Water is more accessible, right? You can just go anywhere, like fill whatever that is with water and measure the pressure. Why do we use mercury? Any ideas? No? None? What is important here is the height. You want to keep the height as small as possible, right? Because you want to keep your device as small as possible. You want to move the things, or you want to move this device around to be able to measure the pressure at different locations, right? So what can we do to keep this height as small as possible? We have to increase gamma, right? That's very simple. Gamma for mercury is high compared to water. If you were to use water here, the height for atmospheric pressure would have been in feet, right? Not in inches or millimeters. So we needed a very large or a very long tube to be able to measure the pressure. This actually opens up the discussion for other, opens up way actually the way for other pressure measurement devices that are, all of them work based on the same concept, that the pressure at 2 points that are the same height are essentially equal. We have like the piezometer tube, which exactly the same thing, but we also have this thing called the U-tube monometer. A U-tube monometer looks something like this. One side of it, we have, let's call it point A. We have some sort of gas or liquid or whatever here. We have another type of gas or liquid here. And we know the height from this location and this location. So we have a base location. The idea is the pressure at these two base locations are the same. And the pressure at this base location is pressure inside this, whatever that is, P of A plus gamma of, let's call it liquid 1, gamma of 1 multiplied by H1. It has to be equal to pressure at this location, okay? At this height, which is equal to the pressure at this height. So the pressure at this height is the atmospheric pressure, whatever that is, plus gamma 2 for this liquid, H2. This is, let's call this P0, atmospheric pressure. We don't want to use two A's. So this is a principle that we are using this principle, the same principle we have used for the regular monometer, for a U-tube monometer, to get the pressure here, P of A. So your P of A is going to be equals to your atmospheric pressure, gamma 2 H2 minus gamma 1 H1. Any questions? Let's solve an example. This is one of your books example. It is telling us a closed tank contains compressed air and oil, and the specific gravity of oil is 0.9. Looks like this. This is what you're gonna see. We have a pressure gauge here, air, and oil. And then this is open to the atmosphere. So we have oil here inside with a specific gravity, and we are connecting it to a U-tube monometer, which has mercury inside, and a specific gravity of mercury is 13.6. And H1, which is this distance, is 36 inches. H1. H2, which is this distance, is 6 inches. And H3, which is this distance, is 9 inches. We wanna find the pressure reading of this gauge, which essentially means that we want to find the gauge pressure of air. Okay, so we have the U2 manometer here. This is telling us the pressure here is the same as pressure here. So we have to find the pressure at this location. First, the pressure at this location has to be gamma H2, right? Plus gamma, the gamma of Hg H2, gamma of oil H1, right? Plus pressure of air, which is the gauge pressure. Does it make sense? Hopefully. So on one side we have P of air plus gamma of oil H1 plus gamma of Hg H2. So that's the pressure at this point here. And the pressure at this point is equals to the pressure at the other side of the U2 manometer, which is at the same height. What is the pressure here? Is gamma of Hg multiplied by this height, H3, plus the atmospheric pressure. But do we have any of the gammas? No. How should we calculate gammas? Gamma of oil is a specific gravity of oil multiplied by gamma of water at 4 degrees, which in British units is 62.4. And we have the specific gravity, we should be able to find it. Then gamma of Hg is going to be a specific gravity of Hg multiplied by gamma of H2O at 4 degrees, 62.4. So you plug in the numbers, you should be able to find the gammas. And we have all of the heights. But the thing that you have to keep in mind is that the heights are given to us in inches. So we have to convert them to feet. How do we convert inch to feet? How do we convert inch to feet? Inches to feet? That's inch squared to feet squared, right? What about regular inch to regular feet? Divided by 12. That's it. Exactly. So this one, we're going to have 36 divided by 12, 6 divided by 12, 9 divided by 12. So let's plug in 36 by 12, 6 by 12, and 9 by 12. So we are going to have gamma of Hg, gamma of oil. We have all of these heights, but we don't have the atmospheric pressure. It is not given to us. What should we do for the atmospheric pressure? Think about it. What should we do for atmospheric pressure? It is a gauge pressure. So essentially, atmospheric pressure is 0, right? Exactly. Thank you. So since we are looking for the gauge pressure, atmospheric pressure is going to be 0, right? So we have all the values we need. You just plug in all the numbers, and your air pressure is going to be end up being 3.06 psi or 440 psf. So a U-tube manometer, we can actually use this U-tube manometer to measure the pressure differential between 2 points, which is a more common use of a U-tube manometer. Think of a setup like this. We want to find PA minus PB. Okay, the first thing we need to do, we need to find a level height location, the same height location in the U-tube manometer, right? Find height H1, H2. And the idea here is, the assumption here we are making in the book is that whatever gas or liquid you have here is different from the rest of the system. So this liquid goes up to this height, and the rest of it is liquid B. Does this make sense? Okay. So we know that the pressure at these 2 points are the same because they have the same height, and they are also the same liquid. That's very important, right? They have to be the same fluid or liquid, a gas or liquid or whatever, right? So let's call this point 1, point 2. P1 is equals to P2, okay? P1 itself is equals to gamma 1 or gamma A, H1 plus PA, right? PA plus gamma A, H1. That's P1. P2 is equals to PB plus gamma B, H3 plus gamma A, H2. Okay? If you are looking for PB minus PA, you can move A to the other side, rearrange things, and this is what you are going to get. So the whole philosophy here is that in a U-tube manometer, 2 locations that have the same height and are made from the same liquid or gas are going to have the same pressure. We could actually make things easier here if we just took these 2 points. But the pressure at this point has to be the same, right? These are made from the same liquid, they have the same height. So essentially, we could have said, let's call this new one H4. We could have said PA is equals to, or PA is equals to gamma 1 H4, gamma A H4, gamma B H3 plus PB. Right? It's the same idea, we're just removing some unnecessary calculations from it. Is this clear? Yes? Okay. So, what should we do with an inclined manometer? That's the next question we want to answer. inclined manometer. What does an inclined manometer mean? It is not that hard, something like this. It is inclined. So point A, point B, and this is the interface between liquid A and liquid B. How should we find the pressure difference between the two liquids? And there are actually two fluids. We're gonna have three. Usually, that's how usually happens. That's what usually happens. We have three fluids. So fluid A, fluid B, and then a fluid C, right? So we're gonna have three fluids here and two interfaces. It is not that hard. It may look a little hard, but it's not that hard. The idea was, let's call this point 1 and point 2. The pressure at point 1 and point 2 is the same. So P1 is equals to P2. Okay. Then we want to calculate P1. Let's say this is H1 and gamma of A. P1, P of A plus gamma A H1. That part we have already seen. But what is happening on the other side? Let's say we have the angle, theta, and we also have this length, L. And this height is also given to us. So we want to find the pressure at point 2. We already know that it is PB plus something, right? Is it going to be PB plus gamma of this liquid C multiplied by L? Or what should we do? What is the height we're going to use here? Or what is the length scale we're going to use here? And whenever you were into this type, you saw this type of problems, you have to think about the definitions we use for like pressure, the hydrostatic pressure. Hydrostatic pressure is always a function of your height, right? Or your depth, yeah. The height of this liquid column is this, right? It is very important. So the pressure difference is a function of this distance, not this length, right? So how do we calculate this distance? Pretty simple. Length multiplied by sine of this theta, right? This is the projection of this length on this axis, right? We have this, the angle this length makes with this axis. We want to find this projection with this axis. So it's going to be L multiplied by sine of theta. And if you don't remember from your mathematics, let's say you have two axes, you have this like vector, whatever, and we have this angle. We want to find the projection of this on this axis, the projection of this vector on this axis. We want to find this value, which is going to give us the height. It's going to be this length multiplied by sine of this theta. Okay, so we are going to have L sine of theta multiplied by the gamma of this fluid C plus, we are already given the height here, so we don't have the length to multiply by sine of theta. We only have the height. So it's going to be H3 gamma of B. So we can find the pressure difference in an inclined U-tube monometer. Inclined, it's not a U-tube, it's actually inclined tube monometer. Is there any questions? Is this all clear? Okay. So what will happen if gamma A and gamma B are much smaller than gamma of C? Or what will happen if we have gas here like air, which have much lower gammas than a water that is going to be this your liquid C here? We can essentially assume that gamma A, the contribution of gamma A and gamma B is 0 to this whole thing, because they're going to be much smaller than whatever liquid you have here. But the main condition, the main assumption we are making here is that your gamma C is much larger than gamma B and gamma A. So effectively, what it means that these two are gas, and this one is a liquid, like water and air. And you want to find the pressure difference between these two locations. So PA is going to be, if that's the case, if this is met, let's call it condition 1. If the condition 1 is met, PA is going to be equal to PB plus L sine of theta gamma C. Is there any questions here? Okay. Well, where do we use this concept? Where do we use this equations, essentially? These are pretty useful in finding the pressure differential between 2 points in a pipe or in a wind tunnel. Okay. The next example we want to solve is going to give us that, a specific thing, right? The pressure differential in a pipe. Let's say you have this pipe, and we have a point A here, point B here. You have this kind of tube manometer that is connecting the 2 points. And this tube manometer, let me change it, is filled with a different type of liquid. Let's say water is coming through here. And let's say we have whatever, Hg. Let me see if we're given any. Yeah, no. Okay, we want to find the pressure differential or pressure difference between point A and point B inside this tube. The first thing you want to find is to set this height as your reference height, where the pressure between the two between the two columns are essentially the same. And then you want to measure the distance from that location to all of the surfaces. One is going to be H3, that is the distance between the interface of mercury and water, and this level height is going to give you the same temperature and the same pressure. This is 0.3. Let's call this 0.2. and exactly on the other side, 0.1 and 0.4 here. So what can we say about pressure at 0.1 and 0.2? 0.2 is the interface of water and mercury. 0.1 is only water, but it has the same height. So the pressure at these 2 points has to be equal. What about pressure at 0.2 and 0.3? We have mercury here. This is the interface. And we only have mercury here. So P2 has to be equal to P3, okay? And then we have another interface, which we can write the same relationship for, and that's the 0.5, which is the interface between water and mercury, and the same height in the water column. So P5 is going to be equal to P4. Okay. Well, what is the relationship between this P3 and P5? P5 or P3 is equals to P5 plus gamma of mercury, which has filled this tube, multiplied by your H3, height 3. Does this make sense? Pressure at this point is the pressure at this point plus the height difference. Okay. And from these two, we can conclude that P1 is equals to P3. Let me simplify the equation. P1 is equals to P3. Okay. Based on these two. And then P3 is equals to P5 plus gamma of Hg. So P5 plus gamma of Hg, H3. P5 itself is equals to P4, which is inside the water column. So I'm just gonna put that in. And then we have this relationship. P1 is going to be equal to P4 plus gamma Hg, H3. But what we need here, so we need to find the relationship between P1 and PA, and P4 and PB. And then we're done. We have found the pressure differential between these 2 points. Okay. Both of these are water. Let's call this H1. Let's call this H2, which is equals to H1 plus H3, right? You can see it from the figure here. P1 itself is equals to PA minus gamma of water, H1, right? But as we go deeper, your pressure increases. So P1 is PA minus, or we can write it the other way around. PA is equals to P1 plus gamma of water, H1. So we are going to replace P1 with PA minus gamma of water, H1. On the other side, P4 is equals to PB minus H2 gamma of water, right? And H2 is H1 plus H3. So PB minus H1 plus H3, then plus gamma Hg, H3. So we have the gammas. If you have these heights, then we essentially have the pressure difference. This is PB, pressure differential. And using the pressure differential, we should be able to calculate the pressure drop, right? Pressure drop, which is going to be very important in future. You're going to see pressure drop is very important in the flow inside the pipe analysis. You're going to see a lot about this in your heat transfer course. Is there any questions? Okay, so we have there is one section of your book that talks about the other pressure measurement devices, but this is just a text that you have to read through to become familiar with the other pressure measurement devices. I'm going to assign reading that section as a homework problem. Just give me a summary of different pressure measurement devices that are mentioned in your book. Okay, so we are going to not talk about that here because I don't think there is anything to that that may confuse you. You should be able to figure that part on your own. And we are going to move forward with the calculation of the hydrostatic force on a surface. On a plane surface. Let's look at this container that contains some sort of a liquid, and we have a free surface that this liquid is creating with the outside ambient atmosphere. We are going to have pressure that this liquid is going to exert on the walls of this container. Okay, we can find the hydrostatic pressure itself as a function of the height from the surface. Okay, as you increase the height, your pressure is going to increase. At the bottom, what we are going to get is the maximum amount of pressure because you have the maximum height, and that is gamma H, right? Gamma of whatever liquid that is multiplied by the height. And it has a uniform distribution. Okay, it is uniformly distributed because the assumption here is that this height of the bottom surface doesn't change at all. So how can we find the force that this liquid is exerting on the bottom surface? Pressure is force per unit area. So to find the force that is resulting from a pressure, hydrostatic pressure, we only have to multiply it by area. So F at the bottom, F of B, is going to be P at the bottom, P of B that's being exerted at the bottom, multiplied by the area. And this area is the surface area. So if it's a circular, it's a cylinder thing, your area is going to be like this. If you want to have a three-dimensional perspective, it's going to be pi r squared, right? If it's a rectangular thing, it has to be the multiplications of different lengths we have here, okay? So this is the area. Don't confuse the area. The area is the area that the pressure is perpendicular to. But what makes things a little more complicated is when you want to deal with the hydrostatic force on the walls. The idea is pressure is a function of height. So as your height increases, this pressure increases. At the free surface, there is no pressure being exerted on the walls, right? But as you increase the pressure, as you increase the height or the depth, whatever you want to call it, your pressure is going to increase linearly. because of this equation, hydrostatic pressure. And we're going to have the same situation on the other walls. Okay, how should we deal with this? How should we find the total force that is being applied on this? We cannot just simply multiply it by the area anymore because pressure is not uniform. So essentially what we need to do is to take the pressure that is being applied on a very small element of surface area here called dA, and then take the integral to cover the whole thing, cover the whole surface. So pressure force that is being exerted on this a small element of area that is located at depth h or height h, whatever that's called it. Pressure force is going to be pressure at that area multiplied by that small element of area, right? This is the area of a small arbitrary element that we have defined. Pressure at this specific point multiplied by that area. What is pressure at that specific point? Is gamma multiplied by the depth of that point, which is h. So let's call this d of f. So a small element of force. To find the total force that is being applied to the walls, you just have to take the integral from 0 to h. Gamma h d of a will give you the total hydrostatic force. Is there any questions here? No? So next step is to find a solution for this. But to find a solution for this problem, we want to make it a little more complicated first, as we do usually, and then find a solution. Let's say the surface here itself is not just perpendicular to the bottom surface. Let's say it is inclined. So we have this type of surface. Pressure is always normal to your surface, and it is changing with your height. Let's say this is your free surface here. We want to find the total force that is being exerted by this fluid on this wall. The idea was this height is the determining factor, h, not this length, right? We learned that from the inclined monometer. So this length is not the important factor. This height is, height h. Let's call it y. And what is the relationship between y and h if you have the angle theta here, or angle theta here? This h is equals to y sine of theta. Essentially projection of this length on this axis. So we have that equation, that general form of equation. The only thing that we really need to do is to replace h with y sine of theta. So your f is going to be the integral of gamma y sine of theta dA. Theta and y and gamma don't change based on the element as a function of element of area. They are constant, right? So we can take gamma and sine of theta out, and we're going to get integral of y dA. If you recall from your solid, this equation is the first moment of area. First moment of area. And we can avoid doing this calculation by just having the location of the centroid of your surface, wherever that is, and multiplying it by the area, okay? So essentially, your resultant force, the total force this fluid, liquid, or whatever that is exerting on your wall is going to be a function of, it's actually, we usually call it F of R, is going to be a function of gamma, the inclination angle, sine of that angle, the location of your centroid, and the total area. Again, this area is the area that is coming out of the surface, right? The area that pressure is perpendicular to. So you have to keep that in mind. This is essentially telling us the resultant force is equal to pressure that is being applied to that centroid multiplied by the area. So we are, without even knowing, we are essentially simplifying things. Let's say your centroid is here, UofSC, and the pressure that is being applied here is this much. We are essentially simplifying things by assuming that pressure at each location, at each point, is the same as pressure that is being applied to that centroid, right? We are making things a little simpler. Is there any questions so far? No. Is this getting confusing? A little. Where's the confusion? Do you know where? I mean, it's all right if you don't know where the confusion is and you need to go home and practice. But if you know where the confusion is, you can always ask. Okay. So we already know that to make everything a little easier, we find the centroid, we find the pressure that is being applied on that centroid, right? And then you multiply that by your area, right? The pressure that is being applied on that centroid is actually this, right? This is the pressure. You multiply that by the area. This is assuming, this is helping us assume that the pressure on the wall is essentially a uniform pressure. But where is that resultant pressure is being applied on? What's that point? Is it the centroid or not? And the answer is no, it is not. This force is not being applied on the centroid itself. It is being applied on another point in our system. We essentially, to find that point, we have to find the moment this resultant force is creating, and then set it equal to the moment your pressure force, let's call it F of P, multiplied by a location Y. I don't want to go further than this here because we need to focus on this a little more. It's at the end of the class. So, but at the same time, we need to finish this. Let's actually stop here, and we're gonna continue on the next lecture. Let's just forget about it. Yes. Because I didn't go into it at all. So we're gonna continue next lecture. We're gonna. Don't forget to submit your homework on when that is Thursday. Thursday is the due date before the class. If you cannot come into the class, send me an email and like send a PDF file. If you are coming to the class, please bring a hard copy. And hopefully we'll grade your homework in a week.
When's the next one?
The next homework?
Next
I have to go back to the syllabus and look, but I think it is next Thursday, yeah. So we are going to finish this topic on Thursday. On Tuesday, we're going to solve some example problems. And hopefully by Thursday, you should be able to submit the homework.
Okay. All right. Has the next homework already been posted?
No, not yet.
What about the read sections about different pressures?
It is part of the next homework.
That's part
So it will be a question on that homework.
Okay. All right. Yes, sir.
Sure.